And I just want to recall some points we had discussed yesterday. You remember that you have different processes that are able to capture and release carbon in the Earth system. In the ocean, we have essentially two kind of let's say network of processes. One is driven by physics and chemistry, so and where the currency is the inorganic dissolved inorganic carbon, and the other one is the organic part that involves biology. Is by far the more complex. Is starting by the biological compartment in the global carbon cycle, is quite active and elusive in some sense, difficult to be understood and especially predict. So it deserves a special attention. If you remember, this scheme shows how circulation affects the distribution of CO2. The gas in here, the deep water are known to be rich, CO2 rich, and have the gas, and you go northward or southward in this case, and water colder, and you have creation of deep water again, and some part of the CO2 is already sequestered in the ocean interiors. Then you have the two parts of two components of the biological part. One creates inorganic carbon with a small shelter produced by some diatoms or skeleton or muscles or gastropods create the shell by using carbon. They are organized by using carbon. So they create source carbonate or organic carbon that eventually reach the sediment and is sequestered there. So essentially, we are thinking about two big compartments. One is dissolved organic carbon. The other one is particulate. So biology is much more complex than that. But in principle, we can describe these two pools in terms of their, let's say, attitude. The dissolved carbon is passively transported by current. So if you want to know the distribution of dissolved carbon, inorganic carbon, just look at circulation. Circulation and basic chemical processes can explain completely. If you know circulation, you know which are the pathways of the inorganic dissolved organic carbon. Here is much more complex, but again, you have a organic dissolved organic carbon, DOC, and particulate. You can divide the two pools because one sinks, has an additional velocity which sums with the ambient velocity given by circulation, and the other one is the dissolved is like the inorganic, so it's passively transported. So the difference is that DOC has the vertical velocity associated with the DOC is 0, so is passively buoyant as follows current. POC has in general velocity different from 0. So in all the equation, the transport equation, we have to think about that in case of particulate organic carbon, an additional velocity, sinking velocity, is added. How much, which is the value of this? This is a good question. Depends on the size, depends on the density of the water, depends on the dimension of the particle, depends on many factors. But what is important to think about is that this creates an effective process that draws down carbon up to the sediment, while the other one, as it is, does not contribute directly. But surely, thinking only in terms of a DOC and POC is quite, it implies a strong limitation in how the biological food chain works. You know, you have the primary producers, so the diatoms or the small algae that contribute to a fixed CO2 from atmosphere. So they are the origin of the food for all the other animals in the food chain, from the tiny organisms up to sharks. They are all dependent on that. So if we know how this works, well, all the rest comes along. And the carbon is sequestered, is captured only by this organism. All the rest, they are just reworking existing carbon. Even ourselves, we are eating meat, sometimes fish, vegetables. All they contain carbon. We are not able to live just respiring CO2 or carbon. Carbon is the currency in nature for transferring energy. If you need energy, you have to eat sugar or pasta or rice. You need carbohydrates. Yeah? And fats also have a lot of carbon inside. So the carbon is the base of our food, comes indirectly from this tiny organism. And only these tiny organisms are able to capture CO2 from atmosphere. So this has a paramount importance in the overall carbon cycle. And how are they efficient? How effective they are in capturing CO2? They obviously try to do their best, but there are some external conditions that helps, which are nutrients and light. Light comes from the sun. So if you have sun, you have sunlight available at least in the upper layer of the ocean, and the deeper you go, the less light you have. So this means that these organisms are present and active only in a tiny surface layer, up 100 meters by Fahrenheit. But this is not enough. To grow, to duplicate, they need nitrate, phosphate, nutrients. So the combination, light and nutrient, create the right condition to create a new organic matter. This is the input. The output of the whole food chain could be simplified in terms of DOC, POC. They respire, they have excretion, they have molding, they die. Everything can be partitioned in terms of dissolved carbon or particulate carbon. So whenever you have new organic matter here, sooner or later this end up in these two compartments. This means that our assumption to think about or simplify the whole food chain. This is a simple food chain. You can have much more complex food web where bacteria, viruses, different of animals, different of the birds, the marine mammals are intertwined. So, but at the end, the concept is the same. No matter what kind of process are inside, whenever you have new material here, new organic material here, sooner or later this material ends up in VOC, POC. So, our attempt to explain this in this way can help us understand the role of physics on biology. There are other roles in physical biology, temperature that rules the vital rates, turbulence, and so on. But in terms of carbon, in terms of climate change, we can safely reduce, at least at a first glance, the complexity of biology in terms of particulate and dissolved organic carbon. This is another way to present the previous scheme. You have CO2, dissolved inorganic carbon. You have inputs of nutrients. You have light, as before, and the food chain is here, and at the end you obtain VOC and POC produced in the surface layer where light is available. And then we are here depicted the principal processes that affect both of the carbon pool and surface. We have some vertical migrating zooplankton. So animals move. They are able to move from surface layer down there because they are safer during sunlight. They are invisible, so they are protected. But when they are here, they respire and excrete. So part of the dissolved organic carbon produced here, created here because they eat some animals or large items here. They go down and respire here. So it is an indirect vertical velocity. It's not this one, but it is mediated by organism. This is the physical transport, as we told earlier. So VOC is passively transported. Then you have the gravitational settling. This is velocity, vertical velocities. And you know that you have not a single particle, but the particle aggregate together, create larger particles think if more efficiently. But during their pathways, they are progressively remineralized, regenerated, and the mass is dissolved again. Only a few parts reach the bottom. So you can have big block that goes down, but also small block created by these aggregates that are actively interacting with the environment, and the mass and the speed change with that. So you see, even if this is simple in principle, in practice, you have a lot of processes that are connected to biology, which are not simply, it's difficult to associate with them a constant velocity. Obviously, velocity, this is a big question, how much this WS is which is the right number for that. But there are another important part in this slide. You see? Maybe you can turn this side on. No, the other one. Okay. Better. You see, here you have the vertical velocity, but also the horizontal one. And they have arrows. So you see that, as we told yesterday, circulation redistribute the carbon and nutrient horizontally. So there's first flux vertical, then there is horizontal distribution, and eventually this water can go again in the upper layer with the upwelling, with a divergence zone, with mixing, convection. There are a lot of processes that can affect. But the other point is the time to go back depends on the depth. The shallower is the layer you are interested in, where the two compartments are stored, the faster is the recycling. So if these biological physical processes draw down carbon in a shallow layer, this carbon is not permanently sequestered from the atmosphere. There's a good chance that in a few years this carbon is released again. Conversely, if the processes are able to interest the deeper part of the ocean, the ocean interiors, below 100,000 meters, for example, which is the permanent thermocline depth. Well, in that case, the time scale is 1,000 years. So, we understand that biology is important, but our interest here in these lectures is to see how physics interact in these processes. This is a gravitational process. They are biological processes. You cannot say more on that. But what is behind these arrows? We'll try to understand a bit more, which are the arrows, how the arrows can be scaled, a different scale in the ocean. And so the idea is to see both of the pools in terms of tracer. Tracer is used as a term for temperature, for salinity. They are active tracers. They are tracers that can be transported by the currents, and they have an action on the circulation, because you know temperature and salinity affect density. A density is a state variable of the Navier-Stokes equation, of the equation that rules the dynamics of the ocean. But in our case, fortunately, we are not in this condition. We use the concept of passive tracers. So the concentration of these two pools here are so small that are not affecting the physical properties of the water. Seawater act as these concentrations are none. And so they are called passive tracers. They are purely transported or with some modification velocity by the current. So when we study the current, we can have an idea on how the tracer behaves. And which are the basic processes that move the tracer? Advection, steering, and mixing. You know what advection is? It's the translation of fluid and any accompanying particles or traces by the background flow. You have a current, you have some particles who have properties inside, everything is moving. Steering is in between diffusion and advection. It's a process that draws patches of tracers in narrow filament by contrasting advection, limited diffusion. And we have a very nice picture here. You see, you have the Gulf Stream here. This is the temperature. And you see that the temperature is advected northward. You know that the climate of the Northern Europe is deeply influenced by this advection of heat. So, at the same latitude in Canada and in the UK, you can have very different climate regime, but the temperature is much higher on the European coast compared to the same latitude in Canada. Why? Because you have this warm current that is effectively transport heat at higher latitude there. So advection is a very efficient way to transport properties, in this case heat, and has a very important role in keeping the climate, the global climate, as it is now in the Earth system. But you see, this is not just a current. You know how many meanders, eddies, and patterns that modify this current. It's not just narrow. You see the idealized current in the previous slide, they are just simple arrows. It's not the case. In reality, it's much more complex. We have a general current here, but looking in more detail, you have this kind of coherent structures. They are called eddies. Eddies are all size, not single size. Continuous tear oceanic tracer and along isopixel surfaces, not only in surface, also in depth. Isopixels, the lines of the same density, create sort of tubes where these eddies move and freely move, essentially. And they have a strong impact on the basic scale tracer distribution and influence as well physical and biological systems. And you see, you have large scale meanders, then you have smaller scale features, and you have a blow up of the images. You can even infer that there are even smaller scale pattern inside. This means that the mixing process is not so effective. So we have advection, and then you have steering, where the properties are of different water masses are quite different, are near each other, but they don't lose their own essence, so they keep their value. So you are able to see a cold ring here, a warm ring here, some squirts, some meanders, and an entrainment of colder water here. So everything is interconnected in quite complex way. How the tracers spread. Let's give a vertical look. At the moment we had a horizontal, and maybe you have already heard this word mesoscale. You have already heard the mesoscale term, or Rossby radius of deformation. Okay, the mesoscale is the scale where this pattern takes place, where the stochastic part of the ocean is dominant, where the statistical properties of the ocean are the best way to represent the movement. You cannot have a deterministic explanation of that, but the statistical description of the ocean, which is chaotic, is the most appropriate. We go back a bit more in this direction during this lecture. But this is horizontal. There are different scales, from mesoscales to smaller scales. But in vertical, what happened in vertical? Imagine you have a stratified ocean, 2 layers with different characteristics. Then you have an eddy or 2 eddies, and the eddies create steering, and then you go from large scale to small scale, and then you mix it. This is the turbulent flow that creates a mixing induced by eddy. So this is the eddy mixing. You have a laminar flow, very small flow where turbulence probably doesn't appear. And in that case, the mixing is due to molecules. So eddies are the example of coherent structure and the primary responsible eddy diffusion. You saw in the previous slide that there are structure, coherent structure, permanent structure, that with different characteristics that put them very near each other. So the gradient inside of this structure is higher. Instead, laminar flow creates a molecular mixing that is much more smooth. Don't create this large-scale pattern, but it is effective at smaller scale. And there are a dimensional number that rules the relevant Reynolds number, for example, that rules advection versus molecular diffusion. And generally in the ocean, advection is much more important than molecular diffusion. But when we talk about eddies, probably the things are not so well established, and the eddy flux or the eddy diffusion can have a much more important role. And molecular mixing is the irreversible transfer of fluid across the tracer gradient, which is achieved by molecular diffusion. When you have this kind of process ongoing, you cannot go back without doing yourself additional work. I hope this can start. So this is an animation just to show how the molecular diffusion acts. This is not the case of large-scale motion that you saw in the eddies. This is a level of molecules. And this is due to the thermal energy associated to each particle or molecule. You see that at the beginning we have all the red particle on one side and the blue particle on the other. After a while, the two are intermixed. You cannot separate them anymore. this is good, but we can do a more realistic one where you have ambient fluid and particles that are larger. Even a small POC can be moved and agitated by the ambient fluid. So small particles has their own motion due to the impact of the ambient fluid. And this also contributes them to spread and diffuse. So this is the lower end of the processes. The mesoscale, the large scale circulation, and the eddies are the high end of the diffusion process. So we have the three eddies. Then we have the steering, and then we have, you see, and eddy and steering are working together. Mixing is the lower end, not reversible process. Then we have the general advection. Then essentially take care of the transport of property along the current. Obviously, if you look at the eddies has also velocity associated with them. So advection can be, well, the velocity associated to the eddies can have some turbulent advection too. So in principle, we can separate them. In practice, the two fields has some overlap. But now try to formalize this a bit more. I'm sure you have already seen that, so just to repeat, because it's good for me to introduce again formalism and concepts. So, want to describe in time the evolution of the generic tracer budget in 1D. And so, rho is the density, C a concentration per kilogram or per mass. And this is the partial derivative, if you know that. So, how change the concentration per volume of a generic tracer? This is the opposite of the flux of this quantity. So, if you don't have flux or the flux are zero, no changes in concentration. The conservative traces has this as a property, and this means that if you have an imbalance of the fluxes along our, let's see, preferential direction, in 1D is just one, the x. Then we have strong changes. It depends on fluxes. If you have balanced fluxes, the flux that comes in a material point on one side is exactly the same, it goes out on the other side, no changes in the concentration, no matter how big are these fluxes. So this is something which is quite well known. In case of advection, you have the advective flux that is calculated this way is the velocity by the concentration of per volume of the quantity of the tracer we are interested in. So, just substituting the flux, the advective flux, in the previous equation, we end up in this advection equation that rules how to change the concentration per volume, which, but for sake of simplicity, called C. This is per unit mass, this is per volume. Multiplying density per concentration per unit mass, we obtain the concentration per volume. And this is the typical 1D equation for advection. So it depends on the gradient of U and the gradient of C. This is the derivative. But in one dimension, you cannot have gradient of U, because U is U. You cannot accumulate mass or release mass. So it depends only on the gradient of C. In 3D, you can read it this way, because if you have the term of the advective flux along X dimension, Y dimension, and Z dimension. And this is equal to that. Why? Could you help me on that, or should I recall it? Because we suppose that our fluid is not compressible. This means that the continuity equation for our three-dimensional velocity is this one. So this means that physical meaning of that you cannot compress the water. If some water comes from one dimension, should be balanced by the proportional fluxes in the other. So, and this is continuity explained in physical terms. If you have a multiplication, as here, you can split in two parts of it. One connected with C, and U is here. Then the other, is the derivative of the product, is related to U, V, and W. But the sum of them is 0. So we end up in only one term, which simplifies our lives in some sense. So we can understand that in an incompressible fluid, the time rate of change of concentration depends on the three terms, one by axis, where in each direction two things matter. One, velocity. The other one is the spatial derivative. What does it mean? If you have a strong current, this doesn't mean you have a strong advection. Advection terms, the two components of the advection term, depends also on this gradient. If you don't have gradient and have strong velocity, you don't have advection. If you look at the same point and look at what happened when you have this strong current, but the concentration of the tracer is the constant, you don't see in that point any changes. Because Obviously, the masses are always different, the particles are different, but the concentration at that point doesn't change. What doesn't matter, really matter, is the fact you have the gradient here. So it's as important as the current to contribute the time rates of change of the trace. This, so far so good for advection. Nothing new, but it's important to recap a bit. Then let's go to the other point, molecular diffusion. This is another process that affects, as we saw, deeply affects the dispersal of tracer at small scale. Molecular diffusion is related to thermal agitation we saw in the animation before. Continuous random motion molecules or other small component particles, substances that is associated with heat. The diffusive flux. So this can suggest that there is some dependence of temperature, more or less. Even if the range of temperature of the ocean is not too high, and the diffusion coefficient is assumed quite constant in time. The diffusive flux is defined this way. So is the well-known Fick's law. So that the flux is depending from a constant, which is called molecular diffusivity, and by the gradient in 1D of the tracer. It has some resemblances with the previous one. If you have the velocity here instead of the constant diffusivity here, but the scale are different, and this is constant. The velocity in that case is something that is provided by the momentum equation, by Navier-Stokes. We have to remember that these equations are not, at least advection equation need to have the companion equation for to provide the velocity. Velocity is not provided by advection, but depend of the momentum, or better, depend on the whole set of Navier-Stokes. Well, again, you can introduce this diffusive flux in the equation, the original equation that rules the changes of our concentration in time, and we obtain this, which is known as the diffusion equation. This is 1D, and this is in 3D. Simple. Essentially, we see the dependency of this concentration on the three axes of the direction is ruled by the same constant, which is fully isotropic at this scale. You don't have any preferential diffusion direction due to the constant, but strongly depend on the second derivative of the concentration along the three direction. So if you do have, as we saw in the animation, you have the only horizontal gradient, all the other term vanishes. So diffusion is three-dimensional, but what is really ruling that is this term. A really interesting point, if you look at the animation, we see that every single particle doesn't move as this equation states. You see that the particle was moving in very randomly. But this is the net effect, is a sort of average value. This is as the temperature is the average kinetic energy associated to a gas, for example, or the molecules. Here we have the macroscopic view of the diffusion process. So we are not following the behavior of the single particle. But if you look at the large picture of that, you obtain exactly this. This is a macroscopic process, but is interpreted in terms of macroscopic variables. This makes our life easier, because imagine you have to just follow the dynamics of a single particle. Is impossible. In reality, we don't have only diffusion or only advection. Generally, we can have both of them. We can combine the two in a single equation. This is called Berger equation by engineers generally, or advection diffusion equation. So the time rate of change of our tracer depends on advective processes and diffusive processes. Both of them can work together. And which are the most important? And so physicists are always keen to know by eye to estimate which are the dominant processes. Because generally the equations we are able to write are well known, well established, but we are not able to solve them. Even the Navier-Stokes equation, the rule, all the dynamics of the fluids are known since almost 200 years, but in many cases we are not able to solve them as they are. Even simple equations like Berger equation, they don't have a closed form for the solution. Only few theoretical cases are known, solutions are known. So it is an open question. So if you are able to understand which are the dominant processes, the dominant terms, you can simplify the equation and try to use them to have an approximate description of reality. That, for many cases, is enough to understand and to predict. So we have two terms here, no longer one, and we can also estimate immediately who is dominant, right? Advection or diffusion? And the answer is not simple. It depends on the scale. You know how the scale analysis is done in physics or ocean? We are associate to each variable its typical scale. For example, the derivative here is u as the typical u velocity scale. C is the typical concentration we have. L is the space in which the space scale associated to this process. And here again, let's make an example. In case of large-scale ocean processes, you have that u is, which is the typical velocity of the current in the ocean. In your opinion, how fast is the current in the ocean? Please help me. 100 kilometers per hour? Kilometer. in 1 second, how fast is the current in the ocean? Is faster than wind or slower? Slower. So in the atmosphere, you can have a wind of 30 meters per second. So in the ocean, how much could be? In your 10 too much. One. You can have in special place in the world even something less than 10 meters per second, but very special streets where special conditions happen. But the Gulf Stream has a typical 1 meter per second. And the concentration could be the order. They say, in this case, they say temperature could be degree. The difference of the ocean is degree. And in terms of carbon, inorganic carbon could be micromoles, millimoles. And the scale is the order of the basin, so it could be 1,000 kilometers, 100,000 kilometers, depends, 1,000 kilometers. So you see that if this is 1, this is 1 to minus 3, this is 10 to 5 meter. See, the number is quite small, but this is even smaller because K has, you see, 10 to minus 6. So the two components here, the two terms are small. So the variation of the concentration in the ocean is small. But to assess who is the dominant one, you make the ratio between the advection over diffusion. And when you do that, you lose the dependence on the concentration. So in this case, what matters is not the concentration of the tracer. The Becquerel number rules only or compare only the processes, not is independent of concentration. That's important. You have a very generic number that says if the Becquerel number is much higher than 1, advection dominates. If instead the Becquerel number is very small, diffusion dominates. So we use again the number we had established before. So U is 1, L is 10 to 5, and K is 10 to minus 6. So Becquerel number is here, in case of the ocean, of the order of 10 to 11. So it's much, much higher. So at global scale, advection is much more important than diffusion. This is also taken into account in the models. Whenever you have to create or calibrate and define quantities in a numerical model, you know that advection is the dominant process and diffusion is often left out, just supposing that the numerical diffusion that is connected to the numerical solution, not the exact solution of the equation, has the effect to diffuse the process. So advection is important. Also in the model, advection is explicitly coded and included, and often diffusivity is just implicitly added as a dispersal term. The important part for diffusion for temperature is the fact that you transform the motion in thermal agitation. In case of tracer, this is no longer true. It's just way of distributing molecules within the ambient fluid. Again, going back to that, in case of oceanographic situation, Peclet number is much higher on 1. But in case which is the case in which Peclet number is the order of 1. If this is 10 to minus 6, so we should have very small velocity, for example 1 millimeter per second or less, and very small scale, 1 millimeter. Well, in that case, when you look at a tiny drop of seawater and look at then what happened inside, that in that case, viscosity, so diffusivity is important. So the smaller scales are dominated by diffusivity, advection doesn't matter. The larger scale are dominated by advection. So we cannot drop or discard completely the two terms. But in oceanographic cases where the circulation is known and understood on large scale, well, in that case, the dominant term is advection. The other one is important in small scales. And also for the organism. The organism in a large scale, so the large scale organisms swim, they move, they can move, and they move largely, they don't care about the viscosity of the water, the diffusivity process of the water. The small organisms have much more difficulty in swimming. They are using different technique to move because they are living in a viscous environment where the diffusion or the viscosity term are more important. This is a side consideration, but at the end, the take-home message is, in our case, Peclet number is much higher. So we have to think about that this is the dominant term for oceanographic processes. Then we can extend and expand more realistically the Borger equation for a tracer. So we have the time rate of change of our tracers here. That depends on the first term, which is the advection of, and we assume here that the continuity equation holds, so the fluid, the ambient fluid is non-compressible, and this is the form, the usual form for the advection term. It depends on the gradient and the velocity component here for along the three axes. And then you have the same for the diffusion, so the diffusion term along the three axes. Then we have two more terms. The first is the source minus sinks. If you have an isolated system where everything is defined at the beginning and you have just to rework and redistribute internally what, sorry, sit down a bit. You just redistribute the concentration inside the water, the fluid. Well, you don't need it. But in reality, we talk about carbon many times. So carbon has a lively exchanges with atmosphere. We cannot. We want to see which is the role of the ocean in the carbon cycle. So we are really interested in explicitly accounting in our equation the exchanges with the atmosphere. So in this case, for example, if we are here talking about inorganic carbon, well, these are the exchanges with the atmosphere. So is boundary condition in mathematical terms what happened at the boundary of your domain. Then we have the trickiest part, which is the so-called reactor terms. Many of the tracers connected to the carbon cycle are not constant. We remember that CO2 is not in aqueous form, is not stable. They tend to hydrolyze and transform in bicarbonate and carbonate. So there are rules that govern the distribution, the inorganic carbon in the water that are not stable. So changes in the sources has an immediate effect on the redistributing of the different chemical species in the seawater. And we have to take into account also in our equation. So to see how the concentration of specific tracer, for example, bicarbonate, which is one, is but an example of a passive tracer that you can consider in the carbon cycle. Well, in the bicarbonate, we have to look at the diffusion of bicarbonate. That depends on the gradient and the diffusivity constant. Advection depends on the velocity of the fluid. Exchange with the atmosphere. We know that more CO2 entering, or partial pressure of CO2 changes the overall content of dissolved inorganic carbon, but the partitioning of dissolved organic carbon depends on the thermodynamical constant. So, to have a proper assessment on how the bicarbonate changes, we have to take into account also the dynamical equilibrium of the inorganic carbon in the dissolved inorganic carbon in ocean. And this is known, we have already written the equation, so we have add here a reactor term that explains or justify this kind of changes. This means that you don't have only one equation. To close the system, you should have an external provision of the velocity. So the Burger equation per se has no solution without having velocity added, plus, if you have this reactor term, all the term that contribute to have the whole equilibrium. So in this case, if you want to have the inorganic carbon cycle, you should account for aqueous CO2 and bicarbonate and carbonate. And this is in principle. In practice, equations used for the organic carbon cycle are different, but in principle, this is the message. So you see, this is explained because in R, you see, you have the dependence of the concentration, but all the tracers involved in the reaction, carbonate, bicarbonate, aqueous CO2, all of them should appear here. And so we have to have velocity, external velocity, and also description of the forcing and other equations for the other chemical species involved in case of dissolved inorganic carbon. So this means that we start with a very tiny, small equation, just two formulas, and that's all. We have four terms, but in some sense, this needs to have the velocity, so the Navier-Stokes equation above, and a set of equations that describe the whole system. So now we are in a good position to describe the whole system. In case if you want to move from the inorganic carbon cycle to the organic one, well, the things are much more complex because the equations of biology are not known. We have some biogeochemical understanding. They are very approximated, but much more complex. So the system is much bigger, and the number of variables here is quite large, 50, 60, 100. Okay, this is the formulation that is good for describing in very general way, which is the evolution in time. And so here you have the capacity to cover all the scales, from large to the tiny one. So have the term that depends on the advection, so the large scale, the diffusion, the small one with K, which represents the molecular diffusivity. And we have also the dynamical processes that create the balance, internal balance of the chemical species, and the external flux. This is very difficult to solve. We cannot, generally, we are not able to solve it directly, even with the computer. It's difficult. And that's why some statisticians propose to use some methods to give a look in a more statistically sound way the properties that discriminate the process of mixing in case, without going into detail of the movement of molecules, but just looking at the statistical properties, so average properties of the equation, of the transport equation, in order to have an idea on how the system works when we are moving from advection, but especially when you move from heating, so from steering to mixing. The EDIs has an advection term, mixing has not an advection term, the others are still in between. Now we are exploring this part. How much the steering can, how much in the eddy steering is dominant, how much in the eddies mixing is dominant. And we will treat it in terms, in statistical terms. So, let's start. You know, this is the operational, that is the gradient, and this is the Nabla operator. You know that, imagine. And again, we have the Brugger equation. For the moment, we forget the boundary condition. We forget the reaction. We use just a passive trace. We have a patch passive trace immersion of flowing fluid. We find a partial domain omega. So our concentration is in that small area where this process will take place. This trace or dye is characterized by space and time and is described by this equation. And so we have again the two components, the advecting one and the diffusing one. And we have some additional condition that our fluid is incompressible, so the continuity equation is holds here. This is quite usual. And then you have the boundary condition to this volume. And this means that the volume, and this means that the velocity here, this is normal, and V or U has no vertical component. So U scalar normal, this is versor oriented outside the surface, and this is orthogonal to them. So this is 0. So this means that you can have current on the boundaries, but they are just tangential along the surface. You cannot have something that goes out. And this is true also for what regard the gradient of our tracer. So this is a vector, no? Which is also could be everywhere in the surface, but no component going outside. That means that we don't have fluxes. This is so-called no flux condition. So everything is inside. So this is some simplified way to treat it, but you see this is quite important for our scope. So we have a closed volume. The surface of this volume is called, the volume is V, and the surface is omega, as the sum of those 6 faces. Not that we could be every kind of shape, but for sake of simplicity, a cube could be nice for us. But it's not written here. It's just a graphical presentation that I think. So, to do this, we use the so-called the methods of Mohan. Please, we have to make some calculations, so please follow me. We have the equation right? Now we multiply the equation by simple. So this should turn in, or will turn in, okay, I just multiply the Berger equation by this factor. Now we can recognize, recording the properties of the derivational product or a function. Then this is nothing different that this. Why? Because we have a derivative in time of a function which is at m, for example, and so we have multiplied by, right? This is basic derivation rule. So, I just canceled because I need more space. This means that this term is just okay. Is exactly this. We have the derivative of our tracer with the derivation rule related to the power plus or by multiplied by the internal derivative. The second one is again the same. It's the same thing. This is not derivative in time, it's derivative in space, but the concept is exactly the same. So this turned out to be okay. And this is the most tricky part. This is not easy to manage it. But we can think about this relation. You have mk and the divergence of this term. You can have again the divergence of product, and you have the first term and the second term. The second term is exactly what we have here. You see? So you just make the divergence of the first term multiplied by this plus the first term multiplied by the second term is the typical rule of derivative of the product. The derivative of the first function by the second, and the first by the derivative of the second. It is exactly the same. And what happened that in this part is exactly what we have here. So at the end we can substitute this term with this minus this one, right? Okay, clear? So instead you have this term, we have this term, which is exactly the term I wrote here is this one. Then this is equal to the first minus the second one. And this is what has been written here. So we end up in a four-term equation. Now, as I promised you, we want to move from a deterministic. Yes. Please raise your voice.
Let me try. When you say you're recording, voice is not fine.
I don't hear.
When you say you're recording,
yeah,
from the quarter, it's like you're using the product rule to differentiate.
Yes.
But for the gradient, it's supposed to run on only the first term and shouldn't run to the next term. So it should, I think, be a delta theta. First term.
Help me. What is it? I don't.
Am I right?
Yeah. Please. then,
This one would be the
yeah,
square.
exactly. Because when we have this, right, you have 2. You have also the derivative. So that's why you have the square. That is a good point. And now we are taking the very. But let me finish this demonstration. Let's take this fourth term, the average on the area. So we are smoothing out the differences inside. In some sense, you have average quantities, and we are looking at a statistical property of the equation. This term and this term are cast in terms of the divergence. And you know the divergence theorem that says that the volume integral of the divergence of a vector is the overall flux of the vector on the boundaries. So, this is important to recall that we are imposed no flux condition, right? So, if you use this is wrong, sorry, because this is on volume, it's not on surface. This is a V here, not omega. And when we substitute the divergence calculated over the volume in terms of the flux of the vector on the surface, associated surface, well, we guarantee by definition that the velocity flux and also the mass and the gradient flux is 0. So these two terms, this one and this one, are 0 by definition, because you move from the gradient, the divergence inside, to the flux on the boundary. And the two terms disappear. So we end up in this equation, which, what does it mean? We say that this called average moment of our gradient changes in time depending on the two lower order moments, yeah, multiplied by the moment gradient squared, which is quite useful relation when we use it. And some specific case. One, quite trivial, if m is 1, you see, if m is 1, this is 0. So we obtain quite trivial solution that the average property of the average value of or the total value of our tracer doesn't change in time, so it's constant, which is quite obvious if we have no flux condition. right? So we advection and diffusion, cannot play any role. And so this is something we have defined a priori, but this just confirms that this is true also in statistical terms. This is probably, we don't need such a complex demonstration for that. But the second one is much more interesting, much more interesting. We see that the variance, this could be considered the second moment of our statistical the statistical property, so the second moment of our tracer varies with the square of the gradient, and is ruled by the diffusivity constant. That's important. So this is positive by definition, this is positive by definition. And we have a minus here. So the second moment of concentration must decrease in time. So the variance must decrease in time. The natural evolution of a system where gradients are in, because of this term, which is the kinematic diffusivity, will end up in a constant value, because at the end this should go to zero, and no gradient inside. Everything is mostly homogenized. I would stop here and then tomorrow I'll show you some example of that. But this is important. So we have large scale eddies, we have small scale diffusion, we have this steering process where the properties of the eddies are still retained, but they are more and more intertwined inside. But at the end, and this means that the gradient inside our area are strong. If you look at the first, you can recall the first image, you have this nice swirling eddies in the Gulf Stream. And the properties, the temperature, and also biological, biochemical traces act the same way. They're very near each other, and the gradients are strong. But this demonstration shows that it cannot last forever. On a certain time, depending on this timing constant, this should lead to the reduction of this variability, internal variability of the system. So, and the stronger will be the gradient, the faster will be the reduction. And this means that at the end we should have sort of a standard, second moment, a standard constant value, which is not totally homogeneous, but is not, the gradient are flattened somehow. Okay, thank you, and see you next Monday, right? Okay. If you don't mind, I give you the slide next time, so make this adjustment. There's an error in the integration domain, so I prefer to give you the right one. Okay? Good. Mm.